Hi everybody, this is your Test 3 review, and on Test 3 in Physics 3230, we're covering portions of Chapters 5, 6, and 7 in Schroeder's Thermal Physics. So, this is the third test. The final exam is comprehensive. I'm not going to post a separate review for that because I've already posted reviews for each of the three tests, so you can just watch those other reviews to help study for your final. You can bring an equation sheet, an 8.5 and 11 by 11 sheet of paper, and bring scratch paper and a calculator. I'll give you the constants sheets like I have on previous tests, and if you need the table with the values of the free energies or whatever from the back of the text, I will provide that too. Now, what we're covering is sections 1 through 3 in Chapter 5. We only cover the first part of 5.3 on phase diagrams, so don't panic about that. We covered all of Chapter 6, and in Chapter 7 we were running out of time, so we covered sections 1 through 3 and then section 6 on the Bose-Einstein condensates. So basically we covered the Fermi-Dirac distribution for conduction electrons, and then we covered Bose-Einstein condensates. Okay, so Chapter 5. First three sections, we covered the free energies. These are the thermodynamic potentials, and each one is useful under different circumstances. Remember, Schroeder provided this little graphic here. If you wanted to write this on your sheet, that's a helpful way to remember the formulas for the different free energies. So here's their definitions. Of course, we already talked about the internal energy, U, and the enthalpy, H, which is U plus PV. We discussed that way back in chapters 2 and 3. But F and G are new to us, and F was the Helmholtz free energy and G is the Gibbs free energy. The Helmholtz free energy is defined as U minus TS, and the Gibbs free energy G is U minus TS plus PV. Now, they're useful under different circumstances. So, for example, the enthalpy, if you do a delta H, could be written as Q plus the other forms of work. So in the absence of other forms of work, the change in the enthalpy is the heat necessary to make the reaction occur, or in reverse, the heat released. And that is useful for basically constant pressure processes. Now, delta F is useful for constant temperature processes. F is equal to Q plus W minus T delta S. And so you can say that delta F is less than or equal to the work at constant temperature. So F is the energy that you need to create the system, not considering the heat that's transferred isothermally, and it's useful for constant temperature processes. Delta G, the Gibbs, is useful for constant temperature and pressure processes. So that is Q plus the other forms of work minus T delta S. So that means that delta G is less than or equal to the other forms of work under constant temperature and pressure. And remember that we can relate the enthalpy and the Gibbs via the formula delta H minus T delta S is equal to delta G. So what you need to be able to do from this chapter is know how to calculate those changes in the Gibbs free energy for a reaction using the values from the table. We did some of these for homework and examples in class. So, for example, this is one of the examples that we did in class, which is the glucose reaction here. And so basically, remember that you have a Gibbs free energy of formation for each of these molecules here. And then to find the delta G for the reaction as a whole, you do the delta G for the products minus the delta G for the reactants. So it's basically delta G for the right-hand side minus delta G for the left-hand side. And that gives you delta G for the reaction as a whole. Okay, now our thermodynamic identity is something that you should memorize, I think. The thermodynamic identity gives you the change in the internal energy for a process, and it's du is equal to TdS minus PdV plus mu dN. But if you're looking at other circumstances, then you might want to be interested in the other free energies instead of du. They might prove more useful, for example. So, for example, the thermodynamic identity for dH is dH is equal to TdS plus mu dN plus VdP. Now, how you do this is you take your expression for H, right? And then dH would be du plus dP times V plus P times dV. And then you sub in for du in your thermodynamic identity and things will cancel out. And that's how we arrive at the thermodynamic identity for H. You should be able to do this for any of the free energies, okay? So I think that you should memorize the top one for du and then derive the others from the definitions of H, F, and G. And that'll save space on your page and it doesn't take long, but that's really up to you. Now, from these thermodynamic identities, you can get some useful partial derivatives. And basically what you do, for example, with this one with DH is TdS plus mu dN plus BdP. If you hold N and P constant, then dN equals dP is equal to 0. And that just leaves you with DH is equal to TdS if N and P are constant. And so you can divide out both sides by ds, and then you have the partial of H with respect to S holding N and P constant equals T. And so you can do that for all of the elements in the thermodynamic identity for DHC, and you can get these three different partial derivative relationships. So for the test, you should be able to do that, and you should also know those Maxwell relations. Remember, the Maxwell relations are if you change the order of the partial. So, for example, here the Maxwell relations you might want to do if you're holding N constant, for example, is you might want to do the partial with respect to P of partial H with respect to S. And then you could flip the order that you take your partials, and that'll give you a Maxwell relation. And those things are equal. So just review those in the test. For the test. We did some homework questions on it and some in-class work. Now remember that maximizing the universe's entropy means decreasing the free energy of the system. We proved that those were equivalent statements. We also covered extensive and intensive quantities. Extensive quantities are quantities that double if you double the amount of material, and they include things like the volume, the number of particles, the entropy, so on and so forth. Intensive quantities don't double if you double the amount of material. They remain unchanged, like the temperature and the density of a material, like a mass density, for example, or the chemical potential. So things like that. And then we came up with the way to kind of wrap our heads around what the chemical potential and the Gibbs. It's the Gibbs free energy per particle, because you could write G is equal to N mu. So that's one way to wrap your head around it. We also covered phase changes and phase diagrams. So a PT diagram is a phase diagram, and it shows all three phases of matter. An example is shown here on the slide for the phase diagram of water. And what happens is you have these lines on the diagram, and those lines represent places where the two phases can coexist. So for example, this line that's labeled S-V is where a solid and a vapor can coexist. The LV is a liquid, vapor, and so on and so forth. And then in between those lines on the diagram are where you're going to have the different phases. So for example, between the axes and the SV and the SL lines, that's where you're a solid. And then your vapor is over here in the pink, and the orange is the liquid. Okay? Now, at the triple point, which is where those three lines intersect, all three phases can coexist. So you can have boiling ice water, which would be pretty cool. Now, as the pressure and temperature rise, the gas becomes dense, and the differences between the gases and liquids at these temperatures and pressures are less marked. And the point where you really can't tell the difference anymore is called the critical point, and that's shown here at top right of this diagram. We discussed the fact that when evaporation and condensation processes are in equilibrium, that the vapor just above the liquid is saturated, and the pressure at that point is the saturated vapor pressure. A liquid will boil when its saturated vapor pressure equals the external pressure. And we showed that in a demo by boiling room temperature water by putting it inside a bell jar and pumping out. We also discussed vapor pressure and humidity. Remember, the partial pressure is the pressure each component of a mixture of gases would exert if it were the only gas present. So, for example, in air, you've got about 80% nitrogen and about 20% oxygen and trace amounts of other things, but roughly that. So the partial pressure of nitrogen and air would be about 0.8, right, or 80%. Okay? So you can... You need to know that so that you can understand the formula for relative humidity. Relative humidity is the measure of the saturation of the water in the air And so that's the partial pressure of water that's actually in the air at a given time divided by what the saturated vapor pressure of water would be times 100%. And remember that human beings like a certain level of relative humidity. If it gets too humid, it's hard for our sweat to evaporate and we feel all gross and muggy. And if it's too dry, then we get a sore throat and we have sinus problems like in winter. Okay, so that was Chapter 5 stuff. Let's move on now to Chapter 6. And Chapter 6 concerned Boltzmann statistics, which are used primarily to describe the ideal gas model. So let's first discuss what the probability of a state S would be if the system was allowed to draw energy from a reservoir at a temperature T. And that is given by this formula here. The probability of that state will be 1 over Z times e to the minus es over kt. Now, let's discuss this. Remember, z is the partition function, okay? And then this e to the minus es over kt, that's called the Boltzmann factor, okay? And sometimes 1 over kt is symbolized in your text with beta, okay? So you could write it as 1 over z times e to the minus beta e sub s. Here, E sub s is the energy of the state, K is Boltzmann's constant, T is the temperature in Kelvin. Now, your partition function you can find by summing over all of the Boltzmann factors. So you just do a sum over all your Boltzmann factors, you find your partition function, and then you do 1 divided by your partition function times the Boltzmann factor to find the probability of a particular state. Now, these statistics work well on classical systems, and like I said, we usually use them for ideal gases. Remember the nomenclature that I taught you, the new jargon, they describe what's known as a canonical ensemble. Okay, so that's statistical mechanics talk, and that means the system is in thermal equilibrium with the reservoir, and so it's allowed to exchange energy until it comes to thermal equilibrium, right? But it's not allowed to exchange anything else, right? It's not allowed to exchange particles. Now, remember, this sum for your partition function is the sum over all the states. Okay, so that means that if there's degeneracy, then it's going to appear in that sum multiple times. So if that's the case, then what you do to find your partition function, for example, is that you sum over all your Boltzmann factors times the degeneracy for that energy state, okay? So for example, for a hydrogen atom in the ground state, your quantum number is NL M sub L equal to 100, and then you have a spin up and a spin down particle in that state. So the degeneracy for that state would be 2. And then for the n equal to 1 state, you'd have a different degeneracy. And remember, we went over some formulas for that. And then sometimes the degeneracy will be given in the text of the problem too. But just remember that when you sum over your partition function, you multiply the degeneracy times the Boltzmann factor, okay? And remember, the definition of degeneracy is energy states that have the same quantum, or that have different quantum numbers but the same energy, okay? All right. Now, once you have your definitions there of your Boltzmann factors and your partition functions, you can use them. They're very powerful to find average values for any variable. And so what you have to do that is do your sum like you're doing a probability, but now multiply the Boltzmann factor times the average, or times the variable. So for example, if you wanted the average value of x, you would do 1 over your partition function times the sum over all the states of your variable x times the Boltzmann factor for the state, okay? And that means that you could calculate your average energy, E bar, by doing 1 over your partition function times the sum over all the states of the energy of the state times the Boltzmann factor for the energy. And of course, remember to multiply by the degeneracy. And that means that for your entire ensemble, your number of particles, big N, times the average energy would give you your internal energy. Chapter 6 also covered the partition function for rotational states, okay? So remember that from your introductory physics classes, rotational energies are given by the angular momentum magnitude squared divided by 2 times the moment of inertia. And so if you plug in for what the quantum values of the angular momentum of a rotational state would be, then that gives you the following formula for the rotational energy levels. H bar squared over 2 times the moment of inertia times J plus 1. Now, J is the rotational quantum number. Its values start at 0 and go up in integer steps from there, okay? Remember that your book uses the notation epsilon sometimes to symbolize the factor h bar squared over 2I, okay? Now, what happens is you have these rotational energy states, and if it wants to jump in between energy states, then one way to do that is to emit or absorb a photon with an energy equal to the difference in the energy levels. So the energy of the photon would have to equal to delta E of the rotational state. If you do a delta between neighboring states, for example, J plus 1 and J, then that would give you a formula for the energy of the photon of 2 epsilon J. Okay, we found the partition function too for rotational energy states. If you have a diatomic molecule with two different atoms in it, like carbon monoxide, then the rotational partition function Z is kT over epsilon. But if you have a molecule like nitrogen, diatomic nitrogen, N2, then your partition function is half that of something like carbon monoxide, so it would be kT over 2 epsilon. We also, in class, derived the useful relationship that we hit a bunch of times, that the average energy E bar is negative 1 over Z times the partial of Z with respect to beta, or the negative partial with respect to beta of the natural log of Z. And we also proved that the equipartition theorem only works well when the energy can be written as a function of the position or speed squared. Those are quadratic systems. Remember that the equipartition theorem says that for every degree of freedom, you get kT over 2 of energy. We derived the Maxwell speed distribution in Chapter 6, and that's shown here. The probability of a particle having a given velocity can be found by m over 2 pi kt to the 3/2 times 4 pi v squared times e to the minus mv squared over 2 kt, and that will give you the distribution functions that you see here. In this plot are the probability densities plotted out for different molecules, helium, neon, argon, and so on and so forth. And you can see that what happens is that lighter molecules will go faster at the same temperature than heavier molecules. From this distribution function, you can see that it's not symmetric. And so that means that there's different speeds that could be used to describe what the speed of a molecule is on average in that distribution. So the most probable speed would be the peak of the distribution curve, like the top of this purple curve here. That would be the most probable speed for xenon, for example. And that is V max probability would be the square root of 2 kT over m. The average speed is just what you would assume. You integrate this distribution function here times V over all possible values, and you get that the average speed is equal to the square root of 8 kT over pi m. Your root mean square speed we derived from the equipartition of energy by setting 1/2 mv squared equal to 3/2 kt. And that gives you your root mean squared speed, which is the square root of 3 kt over m. Okay? All right, now to describe the full partition function, we first discussed how we were going to talk about quantization of these energy states and to figure out how many energy states we have. So what we did was we used a particle in a three-dimensional box from your intro quantum mechanics class as a starting point for all of our distribution functions. And so if you're confining a particle to a one-dimensional box, particles are really waves, and so what happens is standing waves will form, okay? And you can find what the wavelength of the standing waves would be by taking 2L over n. N here is the energy level, okay, and L is the length of the box. Now, given the formula for de Broglie wavelengths, you can find the momentum, which would be plus or minus h over lambda from de Broglie's formula, which would give you plus or minus nh over 2L. And then, of course, your energy would be p squared over 2m, and that gives us our formula for our energy levels for a particle in an infinite square well as shown here. H squared n squared over 8mL squared. Here h is Planck's constant, n is the energy levels, which starts at 1 and goes up in steps from there, integer steps. M is the mass of your particle, and L is the length of the box that you're confining it to. So we use that formula in a bunch of our derivations for the partition functions and the distribution functions for Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein distributions. Now, remember the Boltzmann distribution is for classical particles, the ideal gas law, right? So in order for a particle to behave classically, the average separation between particles has to be larger than the quantum length. And the quantum length is really close to the de Broglie wavelength for the particle. Remember, we found a formula for our quantum length, which we called L sub q, and it was h over the square root of 2 pi mkt, okay? Remember that m here is the mass of a single particle, okay, not the molar mass. Don't do that. Anytime you see k, then you're going to plug in the mass of the particle. Anytime you see r, the gas constant, that's when you plug in the molar mass. But m is the mass of a single particle here. Now, the cube of the quantum length is the quantum volume, which is v sub q, and that's h over the square root of 2 pi mkt cubed. Now, what we said was that the ideal gas for, partition function, and this is the full one for n particles, z would be equal to 1 over n factorial times vz internal over vq to the n power. Vq here is the quantum volume. Z internal is that rotational energy state thing usually, okay? V is the volume that it's confined to, and N is the number of particles. Now, if you take the natural log of that expression, ln of z, it gives you N times log V plus log Z internal minus log N minus log VQ plus 1, okay? And then remember that the Helmholtz free energy F is minus KT times log Z. We derived that, and then that's equal to, by definition, U minus TS. So what we did was we used this value of the log of our partition function and our definition of the Helmholtz free energy as related to the partition function to derive the Sackur-Tetrode equation. Okay, so we did that. Remember that the Sackur-Tetrode equation is for a monatomic ideal gas, so that Z internal thing went away because there'd be no rotational energy states. Okay. Now we also derived other formulas for it, such as the internal energy, which unsurprisingly is 3/2 nkt, the specific heat, which unsurprisingly is 3/2 nk, and we also derived the chemical potential, which is given as mu is equal to minus kt times the log of Vz internal over nvq. Okay, so that's a very tobacco auctioneer rundown of what we did for Chapter 6. On to Chapter 7. Remember that Chapter 7, we were starting to run out of time, so we just covered the stuff that I thought was important and that you wanted to do. So we skipped the stuff on the Debye theory of solids and the black body radiation in favor of Bose-Einstein condensates. So the first thing that we introduced was a Gibbs factor. Okay, now in Chapter 7, instead of just dealing with exchange of energies, right, we dealt with the exchange of energy and particles with a reservoir, okay? And that meant that instead of Boltzmann factors, we had to use Gibbs factors. Gibbs factors are defined as e to the minus e at sub s minus mu n over kt, okay? So here, e sub s is the energy of the state, mu is the chemical potential, n is the number of particles in that state, k is Boltzmann's constant, and t is the temperature. Now, Gibbs factors will also give you the relative probabilities of energy states, just like Boltzmann's factors at a specific temperature T. So you can see that. Now, we use this to derive the idea that you could find the probability of a single state using your partition function, your grand partition function, and the Gibbs factor. So the probability of a given state is 1 over your grand partition function times your Gibbs factor. Okay? And you find your grand partition function by summing over all the Gibbs factors for your system. Remember that this, a little nomenclature here, is the grand canonical ensemble. When a particle is allowed to exchange both energy and particles with a reservoir, that is described by the grand canonical ensemble, which is the grand partition function associated with that, okay? And remember that Maxwell-Boltzmann statistics are the canonical ensemble and the regular partition function. Okay, we also introduced the grand free energy, or the grand potential, and that would be equal to minus kt times the log of the grand partition function, and the grand free energy can also be set equal to F minus mu n. We showed that n bar is kt over the grand partition function times the partial of funky z with respect to mu. Okay, we talked about fermions and bosons. So, in order to do that, we might first want to review spin. So remember that spin is an intrinsic angular momentum, or, of course, that's equivalent to saying an intrinsic magnetic moment of a particle. Now, the spin of the electron is 1/2, right? It's a spin 1/2 particle. And if you place it in an external magnetic field, that will cause the magnetic moment to want to be either parallel or anti-parallel, which is spin up or spin down for the particle, all right? Now, the electron just happens to be a fermion, but there's also a lot of other fermions. Protons and neutrons are fermions, for example, but there's others too. Fermions obey the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can ever be in the same quantum state. So no two electrons in the same atom can have the same set of quantum numbers. And this, if this weren't valid, what could happen is that all the electrons could radiate energy away until every single electron was in that lowest possible energy state, which would be that 1s state. And that would completely change the chemical nature of our periodic table. So that's an easy way to remember and understand the exclusion principle. Now, it turns out this was originally described by Pauli for trying to describe what was going on with electrons in an atom, but it turns out to be generally valid. So fermions that are occupying the same potential well cannot have the same set of quantum numbers to describe them. And so it's a generally valid statement. And this gives rise to Fermi-Dirac statistics and the Fermi-Dirac distribution function. So here's a plot of what the Fermi-Dirac distribution function looks like for different values of temperature. Okay, and here is what the Fermi-Dirac distribution function is. The Fermi-Dirac distribution function n bar sub fd is 1 over 1 plus e to the epsilon minus mu over kt. Now here, epsilon is the energy of the state, mu is the chemical potential, and of course kt we've discussed before. Now what happens is, if it's cold, then this looks very much like a step function. So as t approaches 0, you get your step function in kind of this blue-green curve that you see here. And as the temperature increases, the step function becomes more rounded off. Now this is for even reasonable temperatures. It just looks like a rounded off step function. And it doesn't approach this exponential decay looking state until the temperatures approach the Fermi temperature, which is ludicrously high, okay, for any reasonable material, okay? Now, the chemical potential for electrons in a conductor can be described by the Fermi energy. So mu is equal to the Fermi energy, which is epsilon sub f, okay? And so your Fermi-Dirac distribution function becomes 1 over e to the epsilon minus the Fermi energy over kt plus 1. And we derived what the Fermi energy was in class. I'm not going to go through that derivation here, but the Fermi energy can be described by h squared over 8m times 3n over pi v to the 2/3 power, okay? And so here h is Planck's constant. M is the mass of the particle in question, which for conduction electrons is the mass of an electron. And n over v is the density of conduction electrons in the material. So you should be able to find the Fermi energy for different metals, okay? And the way that you do that is you start off with the mass density of the metal and then do a conversion using the molar mass into the number of conduction electrons per unit volume. So remember, it's basically just a unit conversion, and then you can find n over v. Once you have n over v, the Fermi energy is pretty plug and chug. Now, from the Fermi energy, you can get the average internal energy of the conduction electrons in the material, and that's going to be 3/5 times the number of conduction electrons times the Fermi energy. We also calculated what we call the degeneracy pressure of a degenerate Fermi gas, and that was 2n E Fermi over 5b, which is 2/3 U over v. And that degeneracy principle is, or degenerate pressure, is due to the Pauli exclusion principle. Basically, they just don't want to be crammed together anymore because they might collapse into the same quantum state. Now, the degeneracy pressure is ridiculously high. It's the kind of thing that you find in a white dwarf, okay? And we went over the white dwarf example. But the bulk modulus is something that's achievable in regular pressures and lab settings, and that's the change in pressure when the material is compressed divided by the fractional change in volume. And remember that you could find the contribution that the conduction electrons make to the bulk modulus of material using the formula 10/9 U over V, okay? And that's going to be about 1/3 on average of the total bulk modulus of the material. Okay, we defined the density of states, and that's the number of states per unit volume per unit energy. I should put in per unit volume per unit energy, okay? And that was symbolized by g of epsilon. And so g of epsilon here is described by this function, pi over 2, 8ml squared over h squared to the 3/2 times the root of epsilon. So the density of states grows as the square root of the energy. Now, if you wanted to get the total number of particles, you can integrate the density of states if you're at absolute zero, okay? And that's because, of course, for a Fermi-Dirac distribution system, at absolute zero, it's either 1 or nothing. It's a step function. So it's 1, the state is populated with a 100% chance if you're less than the Fermi energy, and it's not populated if you're greater than the Fermi energy. So n is equal to the integral of 0 to the Fermi energy of your density of states at t is equal to 0. Now, if you're above t equal to 0, then what you get to get your total number of particles is to integrate your density of states times the distribution function for the Fermi-Dirac. And you integrate that from 0 to infinity at t greater than 0. If you want the average energy, remember that you're just integrating the energy times your distribution, okay, which would be the integral from 0 to infinity of epsilon times g times n f sub d. All right, bosons. Bosons are particles that have integer spin. Bosons can be added or they can be intrinsic. So what I mean by that is you can have a composite boson, which means that the total angular momentum spin is going to be an integer. So something like helium-4 is a boson, even though it's composed of fermions. But you can also have particles that are bosons just in and of themselves, like pions or the Higgs boson. Okay, those things have integer spin intrinsically. Photons also have integer spin, okay, because they have angular momentum. They can either be right or left circularly polarized, okay. So all the exchange or carrier particles for the 4 fundamental forces are actually bosons. So photons, gluons, and the WZ bosons, those all have spin 1. And the graviton is a spin 2. Okay, so your Bose-Einstein distribution function is the distribution function obeyed by bosons. So here, the distribution function in bar is 1 over e to the epsilon minus mu over kt minus 1. Now, as epsilon approaches mu, the average occupation of the state approaches infinity. And that's impossible, so the energy must always be greater than the chemical potential. At low temperatures, all the particles are going to pack into the same lowest energy state. And at high temperatures, remember that all distribution functions approach the value for the Boltzmann distribution because quantum particles behave classically as integers get large, or as energies get large. Okay, now we skipped over the probably more valuable stuff on black body radiation, and we skipped straight to the really interesting stuff, which was Bose-Einstein condensates, per your request. So one example of a Bose-Einstein condensate is liquid helium when you cool it to the critical temperature of 2.17 Kelvin. And what happens at that temperature is that it changes into a superfluid phase, okay, because the helium-4 atoms become a Bose-Einstein condensate, right? They change phase to a Bose-Einstein condensate. Now, this point, this critical point, or critical temperature, is sometimes also called the lambda point or the condensation temperature. Now, it's called the lambda point because the shape of the curve of the specific heat versus temperature looks like a lambda, and we derived that equation in class. We went over how that specific heat came about. Now, what happens at the lambda point and below is, of course, it's a superfluid. One of the side effects of that is that the superfluid has near zero viscosity. And so we showed some videos of what happened to liquid helium at the lambda point. Now, liquid helium isn't a pure Bose-Einstein condensate, all right? They develop pure Bose-Einstein condensates in a lab, but liquid helium isn't one of them because of the helium-3. If you cool it even further to the millikelvin level, then even the helium-3 will go into the BEC phase. But at 2.2 Kelvin, it's not there. We derived the London equation, which is the fraction of helium atoms in the superfluid state, and that's F is equal to 1 minus T over the critical temperature to the 3/2 power. The formula for the density of a Bose-Einstein condensate at the critical temperature is shown here. N over V is 2.612 times 2 pi m k T c to the 3/2 over h cubed. And that's 2.612 over the quantum volume, okay? And Tc here is that critical or condensation temperature. So what this tells us is that the density is 2.612 over the quantum volume, which means that you've got 2 to 3 particles packed into that quantum volume. And that means that since the quantum volume is basically the de Broglie wavelength cubed, or very close to it, that means that the wave functions of those particles are definitely going to overlap. When the wave functions overlap, they lose their kind of singular identity and they become a cohesive unit, okay? And they take on the really interesting properties of a Bose-Einstein condensate at that point. We have created, not we, but, you know, the collective we, the royal we, have created Bose-Einstein condensates in the lab. The first success was with rubidium atoms at very low temperatures, less than a microkelvin. And Bose-Einstein condensates now are still being done in labs to simulate systems such as the core of neutron stars, which they believe might have densities this large. And so you can understand the physics going on inside the neutron star. That they also think that it might very well describe the early universe, that quark gluon plasma, which had a density high enough that even though the temperature was very high, the density was so high that a Bose-Einstein condensate state was achieved. Okay, so that is the tobacco auctioneer tour of your chapters 5, 6, and 7. I hope you found it helpful. And let me know if you have any questions, and I'll see you in class.